So welcome to this lecture. This is the part 2 of the welding processes. In the first part, we have already seen the different kinds of arc welding processes and the gas welding. And we are now going to see some more different other kinds of welding which are suitable in some special cases. So first, I would like to show you the electroslag welding.
Hey guys, welcome to SkillLink. Up until now, the welding topics which we discussed had something in common. They were all used for welding medium to thin metal bars or sheets. But what if we want to weld thick materials, say materials with thickness over 30 mm? Such materials cannot be welded together with conventional welding procedures such as stick welding or TIG welding or even gas welding. Instead, we use a different type of welding procedure called Electroslag Welding. This method uses the same basic equipment that is used in most arc welding operations: an electrode and the power source. Similar to MIG welding, the electrode is fed into the welding pool from a winding. The welding procedure is as follows. The two materials that are to be welded are clamped together by a molding shoe. A small gap is left between the workpieces. Below this gap, a base plate is then placed below the gap, sealing it shut on both the sides with just one opening from the top. A flux material is then added into the gap. After this, the electrode is lowered into this particular gap. One end of the power terminal is connected to the electrode and another end is clamped to the base metal. An arc is initiated between the electrode material and the flux. Due to the high temperature of the arc, the flux material is melted. More flux is added into the gap till the molten slag reaches the tip of the electrode. After this, the arc is then extinguished. The main reason why the flux is added here is that it is a very bad conductor of electricity. Because of this, when the current is passed through the molten slag, joule heating occurs. This causes the electrode wire, which is in contact with the flux, to also heat up, causing it to melt and join with the flux weld pool. Since this procedure does not purely depend on arc generation, it is commonly not considered as an arc welding procedure. Instead, it is considered as a fusion welding process. The mold which is used to hold the entire weld pool is normally water-cooled. Since the density of the slag material is much lesser than the molten electrode material, it stays on top of the weld pool. This aids in continuous generation of heat as well as protection of the weld pool from oxygen and other atmospheric elements. While welding very thick materials, the holding die is moved along with the weld pool as it increases in size. Since most of the metal at the bottom would have solidified, this wouldn't be a problem. The electrode feed can also be increased by adding more than one electrode wires into the joint. Due to this specific reason, thick metals can be welded together quite easily with the electroslag welding process.
So I hope you have observed the process, and remember here continuously electrode filler material is fed in the form of electrode here, as you can see, because with the heat this electrode material consumed and form the metal that is ultimately solidify and join between these two region. And continuously, like in case of MIG welding, this electrode is continuously supplied. Okay, and the flux material which was initially poured in that place, that is generally lighter. Okay, that is why that stays in the upper surface, and that actually restrict any further oxidation into that particular material. And this is what is the process, and you can understand the most important thing that you have to remember when you have to join two very thick metal pieces, very thick metal pieces. In that cases, this electroslag welding is suitable. Okay. And stick welding, in the initial of the lecture that has been mentioned, by stick welding, basically the manual arc welding that we are going to do in our workshop, that is basically the stick welding. Okay, so that is not suitable in those cases when the metal pieces are very thick, like more than 30 millimeter, as mentioned in this video. Okay, so after that, we'll see that next kind of welding, which is thermite welding. Okay, so let us see what is thermite welding. That is also very interesting, and again this thermite welding is suitable for welding to very thick metal pieces. Okay, let us see what is thermite welding, and after that I will again summarize the important points related to thermite welding.
Hey guys, welcome to SkillLink. Welding processes are often called in many names. Shielded metal arc welding is called stick welding, while gas tungsten inert gas welding is called TIG welding. Similarly, exothermic welding is called thermit welding. Thermit welding is a type of welding procedure which uses molten metal to join two thick bars of metal. Thermit welding is most commonly used in welding two separate rails in train tracks. Unlike most other processes of welding that we've discussed up until now, thermit welding does not use any electricity for welding. This makes it suitable for welding work at remote locations. The heat required for welding is mostly created by exothermic chemical reactions. The most commonly used exothermic reaction involves aluminum dust and oxides of any other metal. Aluminum dust reduces the oxide of another metal, as pure aluminum is highly reactive. The most common reactant is rust, which is also called iron oxide. When this mixture is ignited with heat, the components undergo a redox reaction. The oxygen from iron oxide splits and joins pure aluminum to form aluminum oxide. During this process, huge amount of heat is generated. The pure iron melts due to the intense heat generated and fills the gap provided in between the rails. As we mentioned, thermit welding is mostly used to weld railway tracks. One of the first railroads to identify and use thermit welding was the Delaware and Hudson Railroad of the United States in 1935. The weld quality of chemically pure thermite is low due to the low heat penetration into the joining metals. Another drawback of this is that pure iron is used to fuse two rails together as opposed to strong steel. To avoid yielding pure iron, a few pellets of high carbon alloying steel are added into the thermite mixture. To get a proper railroad weld, the ends of the rails being welded are preheated with the help of a gas torch till they start to glow in orange color. This is done to ensure that the molten steel from the thermite cauldron is not chilled instantaneously on touching the cold rail tracks. The welding process is as follows. A gap in the rail track is identified. Two mold clamps are placed on either side of the rail, just above the gap in the rails. The entire mold is then sealed properly with packing sand to prevent leaking of the molten metal. Slag basins are provided on both the sides of the mold to collect excess metal and prevent overflow. The entire thing is then heated with the help of a gas torch to get them heated up. They are heated till they become red hot. A metal container or crucible is then placed over the mold. This container is filled with thermite. The entire mixture is then ignited, which causes a rapid exothermic reaction to occur. The heat causes molten metal to flow through the mold and settle down on the slag basin. Once the exothermic reaction in the crucible settles down, it is removed. The packing sand, slag basin, the mold, and the clamps are all removed. The main reason why this procedure is used in rail tracks is due to the remote location of rail tracks. The same welding work can be done with Electroslag Welding too, but carrying all the bulky equipment around for long distances is not very feasible. Finding a suitable power source is also a hard thing. This is the reason why thermit welding is preferred in this case. Well, that's it for this video, guys. We'll meet again in the next one. Until then, bye.
So you can understand that for the railway track welding, the Thermite welding is the most preferred welding procedure. And it is not that only the iron oxide that is there, as mentioned in the video, that other alloying elements are also mixed with the Thermite mixture. Okay, so that it is not the pure iron that actually come there, because the railway track is not made of the pure iron. It's made of the alloy steels and different kinds of alloying elements. Those are also mixed with the Thermite mixture, so that those alloying elements are in the right proportion in that particular joint also. Okay, again you have understood that Thermite welding is again another very interesting, and the heat source here in case of Thermite welding is not the electrical one. Here the heat source is the chemical reaction. So exothermic reaction that produces the heat to produce iron, and that will be melted. Okay, so after Thermite welding, let us see what is the next. Next one, we'll see the solid state welding. Okay, the solid state welding we'll see, and first of all we'll see what is the friction welding. As you can see from this figure that there are two metal plates, and if you rub two metal plates along with the pressure in the direction as shown in the figure, then it is clear that if you continuously rub, if you rub your hands, that the heat is generated. Exactly in a similar way, if you rub these two surfaces, and practically these two surfaces are not completely smooth, there are a lot of irregularities at the joint. So when you are rubbing, a lot of heat generation because of friction will be created, and that is the source of heat. And at the same time you are giving the pressure, and that is why ultimately these two metal pieces can weld. And this kind of welding is what is called the solid state welding. So let us see that how solid state welding works. So friction welding first.
Friction welding. Friction welding is a solid-state welding process in which the heat required to produce a weld is developed by the mechanical friction generated at the interface due to the relative motion of the metals to be welded together. The resulting bond is as strong as the parent metal. Unlike arc welding, friction welding does not make use of filler metal, and the process can be automated. Working principle. When you rub a surface against another surface applying some pressure, you can feel that after some time the repeated rubbing causes the two surfaces to get hot. This is because all surfaces, despite they look smooth and flat to our naked eyes, all surfaces have some irregularities at the microscopic level. Hence, by relative motion between two rough surfaces produces friction, and therefore, heat is generated, and if considerable pressure is applied with rapid relative motion, then the heat generated is considerable enough to cause the material to get viscous at the contact point, and the relative motion is carried out in such a way that it causes the mixing of the two metal at the point of contact and then fuse. Upon cooling, a bond is generated. There are different types of friction welding processes. If you are new to this channel, click on the subscribe button and turn on all notifications. Types of friction welding processes. Rotary friction welding. Linear friction welding. Friction stir welding. Rotary friction welding, or inertia friction welding. In rotary friction welding, one metal is held stationary and the other is mounted in the spindle and made to rotate at a very high speed. Then the two workpieces are made to contact each other with the continuous rotation of one of the metal, and the axial force is applied to both the workpiece. This combination generates friction at the interface, and a weld is generated at the interface. Linear friction welding. In linear friction welding, one piece is held stationary, while another piece is made to oscillate at a very high frequency relative to the stationary workpiece. This vibration at the interface generates heat, and the oxides or the contaminants on the surface is displaced and burnt off due to friction, and this heat also causes the two pieces to heat up and defuse into each other, causing them to weld together. Friction stir welding. In friction stir welding, a non-consumable tool just like a drill bit, but with no cutting edges used, the tool is rotated at a high speed in a spindle, and made to contact at the interface of the two workpieces to be joined. This causes the metal to get heated up and becomes viscous, and then the metals get diffused into one another, and the tool is moved linearly, causing a weld throughout, just like an arc welding process. Advantages. As the two surfaces move relatively, therefore, the relative motion displaces the oxides, and contamination on the surface is burned off before the weld, thus producing a good weld quality. Dissimilar materials can be welded together. No filler metal, and hence no flux is needed. No fumes or toxic gases are generated. Can be used to weld the materials which otherwise cannot be welded by conventional fusion welding processes. The process can be automated. The process is fast and can produce a good quality weld in a short cycle time. Of friction welding process. Rigid and heavy-duty clamping arrangement is necessary for holding the workpiece, for which may have to drill some holes or make the workpiece of the geometry to grip. Exit hole remains once the welding process is finished and the tool is removed. Large axial force or downward force is necessary for producing the weld. Weld design is limited. Setup cost is high. Application. For welding, tubes, pipings, and shafts. Used in the aircraft industry, marine industries, automobile industries, etc. Used for welding copper and aluminium components in the electrical industry. Used for welding, pump shafts, hydraulic piston rods, driveline, etc. Friction welded equipment are used as replacements for expensive casting and forging. Hope you have understood friction welding process. If you like this video, click on the like button, and if you are new to the
Okay, so we have seen that friction welding is very effective, specifically the friction star welding that you have seen, that without any external energy like electricity or anything, it can be done. Maybe the electricity may be required to rotate that particular tool which is used for the friction star welding, and but at the same time no toxic gases or something is coming out of that region. That is very important, and less energy is basically required for friction star welding. Okay, so this is about the friction star welding. Let's see what is the next. That is the resistance welding.
Resistance welding. Resistance is the property of the conductor, by the virtue of which it resists the flow of electrons, that is, the flow of current through it. This resistance to the flow of electrons creates friction and heat. This heat generated is then used to join the two similar or dissimilar metals by melting and forming a bond between them. Types of resistance welding processes. 1. Spot welding. 2. Seam welding. Spot welding. Spot welding is also known as the resistance spot welding process. It is used to weld thin sheets of metal together by applying pressure. The heat required for welding is generated by resistance to the flow of current through the electrode. Working principle. The welding electrodes are made up of copper, which is a good conductor of electricity. The movable and fixed electrodes of the spot welding machine are held in pressure on either side of a pair of plates to be welded together. As the current passes, it experiences the resistance between the electrode and workpiece contact and generates heat. This heat causes the interface of the workpiece in contact with another workpiece to melt, and pressure fuses the two metals, thus forming a solid bond. If you are enjoying this video, please give this video a thumbs up, and if you are new to ADTW Learn, click on the subscribe button and turn on the notification required. Spot welding machine. Tongs, also known as electrodes. Working of spot welding. When the power is turned on, the transformer supplies the low voltage high current to the electrodes made up of copper. These electrodes are held in pressure against the pair of workpieces to be spot welded with the help of tongs. The current flows from the tongs to the electrodes, as copper is the good conductor of electricity but faces resistance at the point of contact between the two workpieces. This resistance generates the heat at metal-to-metal interface and causes the two metals in contact to melt. Then the pressure causes the molten metal to fuse together, and thus a solid bond is formed. Application of spot welding. Spot welding is used for welding thin sheets together. In the manufacturing of fuel tanks, joining vehicle body parts, radiators, wire ends, etc. Advantages of spot welding. The process can be automated. The process is simpler. No filler metal is required. Low or no fumes is generated. The high welding rate is possible. Limitations of the spot welding process. The initial cost is high. Low strength due to discontinuous weld. The process is limited to the thickness of the metal. Seam welding. In seam welding, the workpiece is supported on both sides by a pair of electrodes. These electrodes are in the form of rollers to produce a continuous weld on the workpiece. Continuous spot welding is known as seam welding. The working principle of seam welding is similar to that of resistance spot welding. Equipment are components used in the process. Seam welding machine and roller electrodes. Working of seam welding. When the power is turned on, the transformer supplies the low voltage high current to the roller electrodes. Made up of conductive materials. These roller electrodes support the pair of workpieces to be welded together. When the rollers are made to contact the workpiece, the current flows easily through the roller electrodes with a low resistance, but experiences a high resistance at the metal-to-metal interface, that is between the upper plate and lower plate to be joined. Thus, high resistance to the flow of current, offered by the pair of workpiece, raises the temperature to the fusion point between the workpiece interface, and a weld is generated in the form of a nugget. Nugget is a weld between the two workpiece interfaces. Application of seam welding process. Welding of transformer, paint containers. Welding of gasoline tanks. Automobile mufflers. Welding of sheet metal tanks. Advantages of seam welding. It can generate a leak-proof weld. The production rate is high. Dissimilar metals can be welded together. No filler metal or flux is needed. The processes can be automatic or semi-automatic. It is possible to weld thin metal sheets with this process. A semi-skilled person can also produce a good weld. Limitations of seam welding. The welding process is suitable for thin sheets only up to a thickness of 3 mm. Since the electrodes are in the form of rollers, they can weld only along a straight line or well-curved path. The process is limited to the lap joints. I hope you have understood resistance welding and its types. It takes lots.
Okay, so we have seen that spot welding and the seam welding, and remember those are suitable for the sheet metals. As mentioned, it is generally up to 3 mm. Okay, so this is again a very important in the industry, typically in the sheet metal kind of industry, and different components which are made of sheet metals. The fabrication work is done by this kind of welding. Now we'll see soldering and brazing. Okay, so soldering and brazing, let us see first that what are the different kinds of soldering and brazing that is possible. After that, we will discuss. So first see.
Hi. In this video, I'll be thoroughly explaining how to solder copper pipe to get a nice leak-free joint. If you're unfamiliar with soldering, you'll be able to solder any diameter pipe after this video with ease and peace of mind. There are 3 steps to solder a copper joint. Step 1 is preparation. Preparation is the secret to getting a leak-free joint. If you skip or half do it, it'll most probably leak and cause damage to your property. So this step needs to be followed very closely. Step 2 is the actual soldering process, which I'll get into details in just a moment. And step 3, which is finalizing the joint. With that said, let's get started. Alright, so the first thing I want to go through are the tools and materials you'll be needing to complete the task. So tool number 1 is a torch. You'll find a good torch at your local hardware store that should cost you between 20 to 50 Canadian dollars. Yes, there are better models out there for commercial plumbers, but if you're a do-it-yourself doing minor work, these will do just fine. To be able to use your new torch, you'll be needing some fuel. There are 2 varieties of fuels for you to choose from. You've got your ordinary propane gas, which you can either find in your camping aisle, which should look like this, or in the plumbing section at the store, or MAP gas, which should look like this. The difference between both of these is that MAP gas burns hotter than propane, which in turn heats up your joint quicker, so it's up to you to choose which one you want to use. Next up is a lighter for your torch. If your torch doesn't have one built in like this, you can either use a dedicated igniter, which can be somewhat costly, or use a $1 Bic lighter like I do. Your pipe and fitting will need to be cleaned from any surface corrosion or dirt that could compromise the joint while soldering. To do this, you'll be needing some sandpaper or emery cloth for the pipe and wire brushes for the fitting. Something else you'll need is some soldering flux or paste. The primary purpose of flux is to prevent oxidation of the base and filler material. Without it, soldering is literally impossible. Here's what trying to solder with and without flux looks like. And the last thing you'll be needing is solder. There are many filler materials that can be used for soldering copper, but the most two common ones are lead solder and lead-free solder. Lead-free solder, which is also known as 95.5, is what's used for potable water lines. When doing copper drains, lead solder, which is also known as 50-50, can be used, seeing it won't come in contact with anyone. So as I mentioned earlier in the video, preparation is key to having a good leak-free joint. The first step to accomplish this is to clean both parts that will be joined together. To clean the pipe, take your sandpaper and sand the portion that will penetrate the fitting till it resembles this. As you can see, there's no more surface spottings, and that's exactly what we're looking for. Next is the fitting. You'll want to use a dedicated size brush for your fitting to get it clean. They most often arrive clean from the manufacturer, but it's important to get the surface roughed up a bit just so the solder could adhere better. If you're a commercial plumber and are cleaning a lot quicker and less tiring. With both of your surfaces now prepped, let's assemble them. But before, you'll need to apply some flux. Applying flux is pretty self-explanatory. All that's needed is enough of it to cover both surfaces that touch, just like this. With your flux now applied, it's time for the actual soldering process, which is step 2. Now the goal here is to heat the portion you want your filler material to be pulled into. There's a scientific term for this, and it's called capillary action. Capillary action is the ability of a liquid to flow in narrow spaces without the assistance of external forces, meaning it'll flow upwards, which is pretty cool. It's imperative to start heating your joint at the bottom first, for 2 reasons. Reason 1 being is if you start heating the top first, your solder will want to float down due to gravity.
So let me stop here and tell you that what is actually done here to make a leak-proof joint in a pipe. As you can see that what is done initially after cleaning, the flux is given with the help of a brush, as you have seen. And the job of the flux material is that when the soldering is to be done at that time, that means after heating, when soldering is to be done at that time, there is a chance of oxidation. Okay, so to prevent that oxidation, this flux is given so that the oxidation does not take place. And one more thing that is different from the normal welding process in case of soldering is that you see that the parent material between which the joint is making, that is not melting during the process. Okay, so basically the soldering process taking place at a much lower temperature. Okay, and the solder is the filler material. As you can see in the figure, the solder that is basically after melting filling up this joint, and that solder having very low melting point. Okay, and this solder material, as mentioned in the video also, that there are different kinds of solders possible, but very commonly used solder is the lead based solder or lead free solder. Both are used. And in case of commonly, it is basically the lead and tin, which is the main component of a solder, which is used for the electrical purpose, for the electronic circuits, where it is generally the composition of the solder. Solder is an alloy, okay, and it is made of lead and tin in most of the cases. Maybe other forms of solders are also there, depending upon the kind of applications. Here you can see the application is not the electronic purpose, but for the plumbing purpose. So maybe a different kinds of solder can be used. Okay, so the important thing you just remember, the parent metals are not melting, but the solder which is melting, so the temperature is quite low. It is not above the melting point of the parent metal, but it is definitely above the temperature of that joint is taken above the temperature melting point of the solder material. And for heating purpose, here you can see some gas torch which is used. Okay, So this is how the soldering can be done. As you can see, the filler material which is used called the solder. Other one that is in case of brazing also similar kind of thing, but remember in case of brazing, the again the parent metals which are to be joined, that is not going to melt like other welding processes. Only the filler material, which is the brazed material, filler material, that will basically melt, and through capillary actions in both cases of solder and the brazing, that will go into the joint. And but the temperature of the brazing is more than that of the solder, that you have to remember. Okay. And for the application, remember, generally brazing or soldering, these are suitable for two dissimilar kinds of metals if you want to join. But definitely for the similar materials also this can be used, but commonly for dissimilar materials these are used.
Hello everyone, and welcome to Jumper Man Tech, where we specialize in HVAC but do everything DIY. And today I'm going to show everyone how to. And the way we're going to make this possible today is by using these special aluminum brazing and welding rods. Here's a better look at our rod. Looks like a typical brazing rod, except how brazing rods are usually flat, this is rounded. To bond aluminum is a very simple process, and we're going to begin by taking our aluminum and prepping it. And the way we're going to do that is going to take some sandpaper and sand down the area where we want to actually weld or braze our connection. Sandpaper will do just fine. If you're an extremist, you can take a... I'm going to use these to hold it in place while I braze my connections. We are now ready to begin heating up the pipe, and these rods have a working temperature of 720 to 750 degrees, so that is our melting point. Propane or MAP gas will do, but today I'm going to be using the MAP gas, as the idea here is to heat up our aluminum to 750 degrees. Remember, we're going to put our heat towards the aluminum and not the rod itself. Once our aluminum is 750 degrees, we're going to take our rod and we're going to gently and consistently go across the aluminum, and we should create our bond. Once we heated up our aluminum and we're not quite sure what the temperature is, we could just take our rod and gently go across and see if it's ready to melt our rod. Alright everyone, this is a very thin piece of aluminum. Let's heat it up, and here goes nothing. If anybody found this video interesting or helpful, please drop a like, comment, and subscribe. I'll catch you guys.
Okay, so you have observed that how brazing is done. Now see, in electronic circuits, which is very common for the soldering, many of you have seen this, or if you are interested, then you have already done this.
Video shows basic soldering technique and the equipment used to solder. There are two main types of soldering iron. The iron to the right has a station which shows the temperature on the display. The controls adjust the desired target temperature. The one on the left works at a fixed temperature but is used in the same way. If you're using a digital iron, then set the target temperature to around 350 degrees C and wait for the iron to heat up. When you're not soldering, remember to keep the iron in the holder. Be careful when you're soldering not to put the iron in contact with the lead. Some soldering irons have PVC coated leads which will melt through easily and pose a risk of electric shock if touched. The best leads to use are made from silicon, which won't melt at the temperatures soldering irons reach. The other item you'll need is of course solder. Solder is a low melting point alloy which flows easily when heated to its liquid state. When it cools and solidifies, it fuses to the surface of a metal at the molecular level, providing good electrical conductivity between two metal surfaces. Solder normally contains flux, which helps the solder to flow.
As you can see here, the lead is to be connected with the board, and for that what we are doing, initially the soldering iron that is placed, and already you have seen it's electrically heated, and so its temperature can be set or it can be a fixed temperature. And after that what is done, that solder which is basically in the form of thin wire that you have seen, and that solder is come in contact with that iron, and the solder will melt and fill the joint. Okay, so this is the common soldering process.
And also helps make a good contact by removing the oxides on the surface of the metals being joined.
So in that case also, for a perfect one, you should use a flux so that the oxidation does not take place. But many cases we have seen that people are not using flux in case of electronic purpose. But always remember, both in case of brazing or in case of soldering, the flux plays a very important role to avoid oxidation or make a good joint in the region. So these are the different kinds of welding processes that we have learned, and finally we'll see the different kinds of welding defects. Okay, so different kinds of welding defects which are possible. In the first picture that you can see, which is the ideal weld, and in the next picture you see that cracks is one of the kind of welding defects, where you can see there is a crack, or there may be multiple number of cracks present in the welding zone. The porosity, you know that it is possible that because of some gas inclusion, and the gas will try to come out of that particular region when it is cooled down. So at that time what happens, that small pores are created. Okay, so this is what is called the porosity. As you can see, within the welding zone the porosity may be there. So because if you can control the proper welding current, if you choose the proper electrode, then by that you can avoid this kind of defects. Now undercut, as you can see that a portion which is at the top here, you can see that is not at that region, basically the metal is not there. So this is what is the undercut. As you have observed, slag inclusion, it is possible that sometimes the slag that is formed, you know what is the slag? Slag is formed by the flux along with the oxygen. This slag material which prevents the oxidation of the welding, generally it floats over the surface, and after that we know by chipping hammer we remove that slag. But sometimes it is possible, because of the motion or the dynamics within the weld, it is possible that some of the slags may be come inside to the weld, and after that maybe the solidification over that region takes place. So some of the slags which are basically very brittle material may be include within the welding zone. So that is definitely degrade the welding quality. Here you can see the overlap. So that is again if the motion of the electrode is very fast or slow, depending upon that, this kind of undercut, overlap, this can happen. So proper welding speed, that means proper speed of the movement of the electrode is also important. Otherwise this kind of defects can take place. Incomplete fusion, you can see that a portion, that region there is no weld material, right? So this kind of thing may happen because of the solidification that takes place in the welding region. Maybe the contraction during cooling taken place in such a way, and your welding speed is very high. In that case, there is a chance that this kind of incomplete fusion can take place. Then incomplete penetration, the similar kind of thing, incomplete penetration, and the spatter, you will find that away from the welding zone. As you can see, maybe this is the joint, and away from the welding zone. In some other places, maybe some of the molten metal that is there. So that is what is the spatter, which is definitely not desirable. So these are the different kinds of welding defects which are possible if you can maintain the proper welding condition. By welding condition, I mean the welding speed, the voltage and the current that we are providing, the distance between the electrode and the joint. All this plays a very important role. And the quality of flux, the electrode diameter, everything plays important role. Okay, and not only that, the source of electricity or source of heating, everything plays important role to avoid the welding defects.